think we can get started. So good afternoon, everyone. So thank you for joining us in this seminar session. So first of all, I would like to thank to acknowledge Lockheed Martin for their support. And the speaker today is Professor Paul Reverdy. He's an assistant professor in the Department of Aerospace and Mechanical Engineering at University of Arizona. So Paul, Professor Reverdy received this Bachelor of Science degree in Engineering Physics and a BA in Applied Math at University of California, Berkeley, and then he continued with his PhD in the Mechanical and Aerospace Engineering Department at Princeton, and then since then he joined University of Arizona, and since July 2020 he's been outside Amazon working on navigation and for a Scout delivery robot. So today he's going to be talking about Lockheed Martin, about a dynamical system framework for flexible and sensor-based autonomous task management. So I'd like to thank everyone for participating, and let's welcome Professor Reverdy.
Thank you, Eleonora, for that great introduction, and thank you all for being here. Yeah, the big story that I want to convey to you here is that we can really push vector field planning and dynamical systems approaches farther than you might think. Usually we think about vector field planning just for coming up with individual motion plans, but the big idea here is that we can actually encode decisions in vector fields as well. As Eleonora mentioned, I am currently on leave at Amazon Scout, so I just want to mention that these are statements that I'm making in my, this presentation consists of statements I'm making wearing my professor hat, and they're not Amazon opinions. But I will tell you a little bit about Scout. So here's a picture of Scout. It's a last mile delivery vehicle. Kind of imagine sort of a large cooler on wheels. This is autonomous and fully electric. So the idea is to really make deliveries to individual homes. Right? These are currently deployed and delivering packages. We're actually delivering things to customers in 4 different cities around this country. And the really core challenge here is autonomy at scale, right? So you can imagine that to make such a system work, you need to scale in many different senses of the term. Here's a little promotional video. I'm not sure how this might get a bit laggy, but it shows you that the use case is basically sidewalk navigation in neighborhoods, right? Seems like this is a bit laggy, so I'm going to just kind of skip through. To get more information, there's a website, amazon.com/scout, and about Amazon Science more generally, there's now this amazon.science website, which has lots of different information. And there are lots of different opportunities for both students and faculty. And I saw when I was preparing for this talk that Maryland Robotics now has a connection with Amazon Lab 126, which is also a nice connection that you guys could take advantage of. So on to task flexibility. So taking off my any Amazon hat, and this is purely academic side work. Right. So the idea here is in terms of I'm thinking in terms of task flexibility. What does this actually mean? Let's set some definitions, right? So when I think in terms of robotics, a task is sort of the fundamental unit of what you might want a robotic system to do. And for example, that might be navigate from location A to location B, right? Navigation in robotics, meaning get from one state to another state without hitting anything on the way, right? But to have autonomy, we really have to have multiple different tasks. Now, flexibility means that you have the ability to shift from task to task as required, and you need to do this in a way that's sort of graceful. Now, I'm going to really leverage ideas in the field of vector field planning, where we think about defining a system velocity given its particular state. Right? And the argument that I'm going to make is that vector field planning flexibly encodes a single task. for example, navigation, right? So I'm going to think in terms of the navigation function framework. So here my robot is a point in some domain, which is a subset of the plane, right? So here's my robot, it's a point mass. And I have a goal, and I maybe have some obstacles, right? These obstacles might be convex, they might be not convex, right? And in the navigation function framework, we have a potential function that maps from the domain to the real numbers that's differentiable, and it has a unique minimum that corresponds to the goal, right? So you get a picture that looks something like this, right? And my goal is down here. And we encode the task by saying that basically that the minimum of this potential needs to be an attractor of the vector field that my state follows, right? So this leads to some idealized dynamics that look like basically just potential flow if you're thinking in terms of fluids, or just go down, follow the gradient here, right? Or if you're a controls person, you have a Lyapunov function, right? And this is flexible in the sense that I can start from anywhere, and I will have a straightforward way of completing the task. Now, I want to augment this and think in terms of what I will call task flexibility, right? So now I have multiple tasks, right? So I might have multiple potential goals, right? One goal and several obstacles. This is basically the previous slide picture. I have a vector field that takes me there, right? But I might also have a second goal, and the vector field plan to take me to the second goal might take me to the other side, for example, of this obstacle down here. Okay. So in a standard framework, you might think in terms of a hybrid system, right? So you'll have discrete modes, and you're going to pick either one of these two vector fields, right, according to some logic, right? So you're going to switch between modes, which is to say which vector field you're going to follow when some logical condition is satisfied, right? And my argument here is that this is rigid, right? And the particular use case that I want you to think about is if the logical condition is difficult to evaluate, right? Whether that's because it's dependent on noisy sensor data or some other information that you maybe don't have cleanly, right? So here's the alternative I'm going to propose, right? So I'm going to propose a continuous action selection framework here, right? So again, in the existing framework, you're going to have to pick one mode, right? So you're either going to follow vector field F1 or F2, right? And in this new framework that I'm proposing and advocating here in this talk is to relax the mode selection process, right? So you're going to take a convex combination of fields, right? With weights, I'm going to call them M1 and M2. Sometimes I refer to these variables as motivations, so they reflect sort of how strongly you're motivated to carry out either one of these two tasks, right? So if you're uncertain, it may make sense to put weight or be motivated to do both fields, maybe not strongly, right? So you might have, so M1 and M2 don't have to sum to 1, right? They might be both small, close to 0 initially when you're not very certain what to do. And then as you get more certain, push M1, for example, close to 1 so that you're really converging on that particular and committing to that particular task, right? And we can let the weights change smoothly to make decisions, right? So as I was hinting at, you'd push if you want to commit to option 1, you'll push the variable M1 to 1 and M2 to 0. And we can do this in a smooth way using a dynamical system, right? And the idea here, and the way that I'm going to implement this is I'm going to have some underlying perceived task value, right? So for each one of these goals, I have some way of encoding how important it is to me. And then I'm going to drive these weights by some, to basically pick the high value option, right? And the mechanism that I'm going to use to do this is based on the dynamical systems mechanism of a pitchfork bifurcation, right? So the fundamental question here is, how do I develop dynamics for these weights given these valuations? Okay, so I'm going to take a dynamical system m dot equals f of mv, embedding a pitchfork bifurcation. Let's see. Right. So in a symmetric case, so this v here is a vector. In the case where I have two options, I have a value v1 for task 1 and value v2 for task 2. In a symmetric case where they're both the same value, I should have a symmetric pitchfork bifurcation, right? So the idea here is that I'm plotting average value as my bifurcation parameter, and a preference for option 1 is reflected at, as sort of this vertical axis, right? And so when both values are low, I don't commit, right? I have no preference, so that's represented in this stable branch here, right? And there's a stable convergence to towards this equilibrium. But if values are both sufficiently high, then I should break this this deadlock situation, right? And basically flip a coin, right? So the idea here is that over on this side, average value is sufficiently high. I have an unstable equilibrium where I have no preference, and I'm going to quickly converge to having a preference either for option 1, or down here I have the symmetric case where I have a preference for option 2, right? And essentially what this is going to do is flip a coin based on the initial state of the system, right? And when I'm asymmetric, for example, if V1 is greater than V2, we're going to unfold this pitchfork bifurcation. You see what happens is this very special critical point breaks to encode a bias for the high value task. And you see, again, in certain regions, we're still going to be converging to something that looks like deadlock. But over here, for average value in this, over in this space, I'm going to converge to a preference for option 1. And so that's the way that this pitchfork bifurcation can encode a switch kind of behavior. Now I'm going to embed this in a system architecture with a block diagram that looks like this. So we have a paper that was just accepted to IEEE TRO in press. I think it should be available on Explore. If not, it's on my website. And the idea here is that this pitchfork bifurcation is going to be embedded here. This is going to give me this M state, which are my convex combination weights. I'm going to use this to weight different underlying vector fields. I'm going to feed this X back up here to a dynamic, which is going to encode what I care about. And this is a valuation. I'll get into more of these details later. Right, so the idea is that the robot vector state follows the weighted sum of these vector fields. Right, this is a convex combination with weights M. These weights evolve smoothly to basically select the high value task using the pitchfork system that I mentioned on the previous slide. Right? So you can think of this as being like a soft argmax of V. And then these values evolve according to the current physical state X and sensor data U, right? So I might have sensor data coming in here. And the way that we encode specific behaviors, high-level behaviors, is by designing these value dynamics FV. And in the next couple of slides, I'll show you examples of behaviors that we know how to encode. Right? So the first one here is a variant of FV that yields a limit cycle. Right? So this is a sort of standard navigation function workspace. So I'm inside, called a sphere world, right? In the literature. So I'm inside. I need to stay inside this large circle. My obstacles are also spheres, or in R2, just circles, right? So I need to avoid this location, and I have 2 goals. Right? And my point robot starts off on one side here. You can see the states on the left. So here are the navigation functions, the motivation traces, and these value states. And what I do is I go first to one location and then to the other. Right? So this is reflected by, you can think of these as normalized distances to the goals. You can see that when the value for goal 1 is high, then the corresponding motivation is also high, and I perform that task. Right? This particular FE is set up so that once I actually reach that location, right, this value will drop. The corresponding value will drop, as you see here, and then all of a sudden the other value is the one that dominates, and then with some hysteresis I switch, and therefore I'm going to go back and forth. This yields a limit cycle kind of behavior. And the beautiful thing here, right, when I'm talking about task flexibility, is that the idea is that by making something which is flexible, it's going to be quite robust. Right? So here, what I've done is I'm using exactly the same control system that I showed you on the previous slide. What I've done is I've removed the obstacle that was here, and I'm going to let this obstacle move. I didn't tell the system that this obstacle can move. I merely have a good sensor. I'm having a model where I have a good sensor, so the system knows exactly where the obstacle is at all times, and I have no actuation limits on the system. Right? So start off doing something similar, and I have an emergent behavior here where, let's see, these might be a little laggy, where essentially as this obstacle is swinging back and forth, still the robot, my point robot, is performing a limit cycle behavior where it's going back and forth recurrently, patrolling between these two locations, and avoiding the obstacle at all times. Hopefully this is coming through. I'll skip to the next slide. So not only can we get numerical results, but we actually have an analytical guarantee that this limit cycle occurs under certain conditions. This was previously published in SciAds. So the idea here is that we have two parameters, right? There's essentially one gain here. There are two gains. You should think of V and lambda as gains, and these epsilons are the inverses of the gain. So as I get closer to the origin, I have higher gains. So think about what happens as I come down along a vertical slice in this plot. So essentially here, what I'm doing is I'm increasing a gain, right? And as we're used to in control, as you increase gains, often things go unstable. In fact, what's happening here is for low gain, we have a stable 6 point where there's a deadlock phenomenon. The robot can't make up its mind, which is actually what we don't want, contrary to what we often want in control. And as we increase this gain, that deadlock phenomenon becomes unstable, that equilibrium breaks, and we get a stable limit cycle. Right? So there are a couple of theorems in this paper that show basically that there's a guarantee that you can always crank the gain high enough. There's some finite value of the gain that will be large enough to create this limit cycle. The analysis uses geometric singular perturbation theory. Now, we want to extend this, right? This is a nice place to start. But a nice place to go would be to have more than two tasks, right? So the decision mechanism that I wrote down initially only accounts for n equals 2 goals. Right? Turns out that the case for n greater than or equal to 3 is significantly harder. Mathematically, what you need is something called bifurcations on the n simplex. So think of this as the space of weights, basically convex weights. There's been some interesting new work that's come out since I initially started this from a couple of other groups, but my particular feasible workaround is to think about parsing things into binary trees, right? So the idea here is that I know how to deal with binary decisions, and so the way to make an n-ary decision is to turn it into a series of binary decisions. So here I want to decide between, think of this as 0, 1, 2, and 3, and the way I decide between these is I split between 0 and 1 on the one hand, and 2 and 3 on the other. And then once I get down to one of these two nodes, I'm going to split again. Right? And I can feed information back up this tree as well. There's a preprint of the decision-making mechanism available on arXiv. And when we actually wire this all together, right, now we have a four-way decision. So I've got 4 different goal locations. And if we let this go, right, there's some initial transient. You see that the system doesn't immediately get to touching all the locations, but over time you converge to this other limit cycle where we actually do repeatedly visit all 4 locations. Right? And there's an interesting question about the topology of the limit set in the sense that we might ask, what is the order of traversal of these locations. And we have some understanding that this is a function of the binary tree topology, and there's some work in prep to try to leverage that, to actually design the trees according to maybe some high-level specification, perhaps encoded in some kind of formal methods language. A second capability here would be to respond to noisy signals, right? So imagine either that you have some kind of foot, for example, a foot planning exercise with a legged robot where you have to decide where to place the feet when you're running, for example. Or you could imagine that you're navigating in a noisy environment and you're not sure where there will be openings in your free space. Okay, so we're going to model this as a very simple task where we have an initial location for our point robot, and we have two different goals, right, that are given here and here. Right? And the idea here is that you're starting at some distance L naught away from this, what I'm going to refer to as the baseline, right, between these two goals. Right? You could imagine that there's an obstacle in between, and you have to decide whether you're going to go left or right. Right? And what you get is some noisy signal that has, if it's +1, you're supposed to go to location 1. If it's -1, you go to the second location. And maybe there's some gain here. And then there's some noise here. Z of t is, for example, white Gaussian noise, right? So your signal to noise ratio is mu over sigma. Right? And the idea here is that the geometry affords you some opportunity to anticipate, right? So initially you don't have any, you don't know whether you need to go to the left or to the right. But regardless of the correct decision, you need to move downwards. Okay? And you need to make a decision as evidence is accumulated. And the idea here was that the core idea here to solve this problem was to design a value dynamics, which takes this noisy signal here to encode a likelihood ratio test, so a very common signal processing detection theory kind of tool. This is also in the TRO in press work. So here you see a turtle bot that has two goal locations. We see, hopefully this is coming through with the webcast. You have a noisy signal that has mean that's changing, showing the range to the different targets here, the motivation states, and the underlying, basically the detector state here, right? So whichever trace down here is higher is the hypothesis that's more likely, supported by the data. And this can be very cleanly extended to include vector field plans that incorporate obstacle avoidance, right? So this is the same controller, and we're just doing beacon homing in the presence of obstacles using a standard obstacle avoidance technique that's detailed in the paper. Another question here would be what performance guarantees can we give, right? So some initial work along these lines was published at the conference last year, RLBM, and there's some new work with my student Henry Lay, which was submitted to ACC, this coming ACC, right? So the kinds of bounds that you want to look at are error rate, for example, the probability that you go to the wrong target. Reaction time, right? So this would be the time that it takes you to decide plus the time that it takes you to act. So that's going to couple your decision time and your the signal processing, which gives you your decision, and your actual physical action, which is going to take you from point A to point B. And perhaps also your distance traveled, right? You can imagine that if you revise your decision too many times, you may end up having to turn around, right? So that may not be desirable. So there are certain trade-offs that need to be balanced here, right? And there's some new results using basically a model predictive control approach to try to tune this time distance trade-off. Yeah. Now, a third capability that we're working on building here is a way of kind of mixing these two together. So we would maybe have some kind of patrol and inspection task here, right? So I might have a patrol. This is a very simple patrol where I'm just oscillating. I'm repeatedly visiting two different waypoint locations. And I may also have some inspection that needs to happen when a certain noisy condition is satisfied, right? And the idea here is, again, that we can use trees as for multi-point patrol. So I'm gonna have sort of a patrol supervisor node here that's gonna implement my recurrent patrol between these two waypoints. And this is going to have wrapped above it an overall supervisor, which will implement on one side, basically the likelihood ratio test kind of detector, and then have on the, as a default non-alert behavior, the patrol behavior, right? So the idea here is, again, when an event is detected, we need to spike the sort of alert value, and then we're going to push the robot to go visit, for example, where the alert happened. Right? So here we're going to start by sort of just very simply oscillating between the two locations. This is my simple recurrent patrol. And then after some time, an event happens up here, right? And then once this has been detected, I'm going to go here, check it out. Once I visited it, the value in staying here, for example, maybe I need to take a certain number of samples so that some other informational criterion is satisfied. But once that criterion is satisfied, I can return to my original patrol behavior. Right. And now to go farther in this along these lines, we really want to find ways to compose different behaviors. We've seen that we can, and we've seen hints of this, right? Basically, particularly in the previous case where we wanted to compose a detection task and a patrol task, right? So this gave us this patrol and inspection. Right? So we want to either do things together, maybe in sequence, right? So maybe I have a series of waypoints, and this hints at maybe trying to build a large limit cycle, as we did for the 4-point patrol. Right? Hinted at by this video here. Maybe we want to do something in parallel, where maybe we have multiple obstacles that we need to avoid. Right? So this is sort of an AND approach if we're thinking in terms of logic. Or maybe conditionally, right? So you could imagine, like here in this investigation, we might want to do a conditional approach. Let me see if it's like this. Interesting question from Pratap. Is there any connection between the binary tree topology and the Voronoi type partitioning of the space? Yes, and that will be. I'll get into this a little bit more in a little bit more detail at the end. There's some questions to answer here. It really has something to do with the way that this is with the way that you actually implement the value functions, right? And so a key open question here is how to develop the appropriate value function dynamics here, and in particular how to program such an FV from maybe like a high level specification, right? So there are ideas here where you might want to use formal methods. You might also want to imagine doing some kind of learning from demonstration. So you might want to learn how the values should evolve, right, from maybe a human demonstration. Right, so looking forward here, I'm just going to recap a little bit in terms of the different possible extensions, right? So we're thinking also how might one do this with multiple different platforms, right? So there's a kind of clear path forward using consensus dynamics, for example, on the value state to coordinate. And there's also some interesting new works that might hint in this direction, trying to extend these kind of bifurcation, decision-making bifurcations to multi-agent cases. Another place where this might be of great interest is in terms of adversarial environments or some kind of game formulation, right? So it might be beneficial to be flexible if you're dealing with the presence of an adversary, right? Whether that's a game against nature or against some other part of the system, right? So you might add noise to your value dynamics to randomize behavior, for example, right? So you might have some fundamental stochasticity in the way that you react. Or you could also imagine trying to make sure that you would switch tasks as you perceive an adversary taking their own actions, right? So you could really inject maybe a payoff matrix information in your perceived value action value state. Right. With this, I want to thank my students Craig Thompson and Henry Lay, and acknowledge that the AFRL has funded quite a bit of this work. And I will take questions, starting with the question from Pratap. Thanks. So I guess people can type other questions in the chat. So first question, is there any connection between the binary tree topology and the Voronoi partitioning of the space? So I'm going to go back here. Between the binary tree topology, so okay, the idea here is essentially, I think the connection would be in terms of how do you declare that you've completed a task. So the idea here is that, and the way that this was encoded. Sure. The way that this was encoded is that essentially the way that you declare a task to be completed and therefore the corresponding value to decay is you have to get within essentially an epsilon ball of that particular goal, right? We could imagine, and it was under those situations. Let me see, I should have an additional slide here that might help explain this. Right. I'm going to share this slide. So the idea here is that the dynamics are the way that I encourage a limit cycle is that basically when I'm so imagine that the way I'm encoding whether I'm close or far from having achieved a task is through this navigation function, which is sort of a normalized distance, right? So when I am far away from having achieved my task, right, this C is equal to 1. So this whole term goes away. This is equal to 0. And I'm going to have stable growth of the value of task I towards some reference sort of value, VI star, right? And this is linear dynamics at the time scale 1 over lambda. When I get close, right, essentially what's going to happen is this is going to go to 0. And if you work out the arithmetic, what I'm going to have is exponential decay at basically VI is going to look like, VI dot is going to look like minus lambda VI. So I'll have exponential decay. And the really key thing here, the way that this would connect up to Voronoi partitions is how do you declare whether you're close or not, right? So you could imagine using a Voronoi partition to refine what you mean by close. Let me see if I can take a look at this. So does that answer the question? Hope it answers the question. Yeah, great. And then in terms of potential extensions to multiple agents, right? So the idea here would be that we have not only one agent, but maybe we have several agents, right? And so let's go back to this picture, right? So here, this might be the picture for a single agent, right? So I have a single point robot that's evolving its own internal state M, which is its weights on its different possible fields, and it has its own perceived value of the different tasks it might achieve, right? So we might imagine that we have not just one copy of this, but we might have N, right? And then the question becomes, how do we want to coordinate such a team? One natural way to do this is to have, so we're going to have interchange on something, right? So you could imagine that you'd want to have, for example, consensus on the values, right? The task values, right? So we could imagine that we have multiple different copies, and then we run some kind of consensus dynamics on these V states here, right? So imagine that this is V sub I for the ith agent, right? And if we have consensus here, then everyone will have consensus on what needs to be done, and then all the agents will have consensus on what they're doing. This may not be what we want, though, right? Of course, you may also want to have a task sharing approach, right? So you could imagine that you have N robots and M tasks, and you may want to distribute those accordingly, right? So you may want to actually encode some kind of dissensus on the value, either at the value state or on the motivations, right? So you may want to push to say that, okay, 2 different people should go here. So the natural way to do this is, again, to think about consensus and coordination using that kind of thing. And this could either operate at the value level or at the motivation level, right? So you could imagine that different agents might have very different information, right? And so you may want to propagate that differently. You may want to retain information locally and only diffuse certain information. It's early days there. You're very welcome. Anybody else? Well, thanks, Todd. Appreciate it.
Are there any other questions? So here there is a new question. Do navigation functions suffer from local minima?
Good. It's an excellent question. So this is precisely the benefit of the navigation function approach. So the idea here is that, let me go back to this picture. I think it's helpful. So what you see, it's well understood that if you want to have a smooth function, you have to have each obstacle introduces a new equilibrium. The key thing about navigation functions is that they are structured in such a way that you can tune parameters so that those equilibria are saddles. So you do not have, so you do have a unique minimum. But it's a very good question.
I do have a quick question.
Please.
So when about the multiple task, okay, so can the sequencing be adjusted in a sense?
Yeah, so this is something that the answer is yes. The next question that you will want to ask clearly is how, right? How can we guarantee something? And this is what is not, we don't have a clear answer on this yet. It's an excellent question, and it is the right thing to ask. We're starting to understand better how the unfolding works of the bifurcation, and it's clearly related to that. And so that's something that's definitely in prep, and that's why this note down here. What seems to be quite clear is that as you permute the topology of this tree, then you do adjust the sequencing. But this is something that like I say, we're still trying to understand how that works out. It's definitely something that we would like to do.
Thank you.
Sure. So it sounds like maybe some of these videos didn't come across as well as I'd hoped. So I'm going to replay this video. Let me know if to me it looks like things are lagging, but I'm not sure if it is for everybody else.
Yeah, it's like
yeah. Yeah, they are lagging. Okay. Well.
So we have a few questions. So someone's asking, is the method designed for Amazon Scout?
No, I want to be clear that this is very much the academic side of things, and this work was predating my connection with Amazon.
Thank you. Any other questions? I might ask another quick one. Quick question.
Please, yeah.
In terms of perturbation, so how can you predetermine? So what is the maximum perturbation range you can tolerate?
Right. Good question. I don't know that I have an analytical result on that. Numerically, the answer is quite large, as is hinted at by this video, which is playing well. So I think for now that's probably the best answer I can give you. There may be some way to analytically provide some insight into that.
Okay.
Yeah. Sounds like maybe someone was trying to ask a question via audio, but I don't know if that's possible.
Yeah, I'm reading a question.
Yeah.
Have you thought much about the issue of trust that a robot will complete its mission?
That's so I guess the question of trust is definitely one that's come across. I guess there are a couple of ways. I guess then the next question is whose trust? I guess the answer is I guess you're thinking of a user or a programmer, right? Somebody who's specifying the mission. Certainly, that's sort of the reason why we try to develop guarantees, right? So the analysis is designed to give you some a priori guarantee that it will work, and therefore you can trust in the sense of you have a proof that it will behave in a certain way given certain assumptions. You could imagine as things get more complex, as the behaviors get more complex, then there might be questions of trust. I don't know, but clearly that's why we work on developing proofs of behavior.
Okay. So we have another question. So I'm thinking of the person who dispatched scouts to deliver multiple packages.
I see. I see. So clearly, clearly this is something that so in terms of the navigation behavior, this is exactly why we want to come up with guarantees. Yeah.
Any other questions? Yes. So your method is analyzed in continuous time. I'm wondering that if the motivation layer dynamics is updated at a different time scale, what will happen?
Different time scale than the, I guess, a different time scale compared to the physical dynamics. Essentially, the behavior is going to be that essentially, as long as the decision dynamics are faster than the physical dynamics, then things should be okay. That's essentially the intuition. So that I think that's the answer. Another question: Have you thought about how this framework can be modified for a dynamic set of tasks? Yeah, good. That's a good question. I mean, and this is something that we've thought about in a purely academic setting for sure. So you have, for example, you don't know ahead of time how many waypoints that you want, right? So how can you deal with that? The simple answer is that you might just build a tree that's big enough to accommodate all of the tasks you might care about, right? And once a task is completed, for example, in here, right? So once you've actually accomplished your inspection mission or task, what you do is you simply add some dynamical logic to reduce the value associated with that task, right?
So another question from the audience: how can a guarantee be quantitative in a highly uncertain environment, like the one Scout will encounter?
In a real world environment, well, you have to make model, as you would do in any case. You make modeling assumptions, and you want those to be conservative, and you make conservative assumptions, and then you prove things based on those assumptions, right? And then you need to be very careful. Okay. Looks like we have another question. Maybe, not sure.
Oh, yeah, there's been a comment that's been added. There's a vandal tip scout over. Always refer to the previous question.
Sorry, what was it?
Yeah, there's just been a note added in, a vandal tip scout over. So I refer to the previous question.
Oh, I see.
Okay. Are there any last questions from the audience? Before we thank again our speaker.
Thanks very much.
Thanks, Paul.
You're very welcome. Thank you. It's a particular pleasure to be here as among friends. Thank you so much.
All right. Thanks, everyone.
Yeah, thanks everyone for participating. Thank you, Paul, for this great talk.
Cheers.
Thank you.